What's up, guys? I made this problem, and I think the main solution that I see here when people try to solve this problem is hockey stick, right? Was it 100? Was it 100 choose 2 plus 98 choose 2 plus until 2 choose 2? Was that yeah? So basically, you would just case bash it and just add up the amount of choices for each square, and then you would multiply this by 2. This is most people's solution, I think. But I won't delve into this a bit. I won't delve into this too much, considering this is not actually my intended song. And what I would like you guys to do is think about what it means for a bishop to attack another bishop. So in a chessboard like this, oh, it actually was grid lines already. Um, the motivation for making this problem came to me while I was thinking of bijections, specifically like bijections in a square. And for a bishop to attack each other, they need to be on the same diagonal, right? And what you can think about is what does a diagonal define? Or like what defines a diagonal? A diagonal is defined, or a diagonal of a square. A diagonal of a square is just defined by the corners of the square, right? So if two bishops are attacking each other, if they're on the same diagonal, that means um you can connect the two bishops like this. And incidentally, connecting them like this always forms a square. Why? Because the bishop always attacks at the diagonal. And if it's on the same diagonal, then that means you can draw a square with two bishops as the corners. So actually, very neatly, the amount of arrangements wherein two bishops attack each other is just the amount of squares that you can make in a grid. Because if you pick any two corners of a square, like let's say, let's pick this square, and we pick two opposite corners, that's actually a unique arrangement of two bishops attacking each other because it's a unique diagonal of the square. So instead of summing all the possible combinations of 100 choose 2 plus 90 choose 2, blah, 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 we can actually just look at the amount of squares um, there are in a 100 by 100 grid. So what would that look like? Well, let's just assume this is 100 by 100. The minimum square, by the way, is a 2 by 2 square. Because obviously in a 1 by 1 square, you can only put one bishop. So if we were thinking of the amount of bishops you can put that are right next to each other, like in this diagonal, you're basically asking how many 2 by 2 squares are there in this grid. Because for two bishops to be right next to each other and attacking each other, they would be the corners of 2 by 2 square. So the amount of bishops in this kind of arrangement would be 99 squared, because that's how many 2 by 2 squares there are in a 100 by 100 grid. And obviously you can kind of guess that um the amount of bishops that would be like one square apart is equivalent to the amount of 3 by 3 squares they are. And how many 3 by 3 squares are there in a 100 by 100 grid? There should be 98 squared. And if you keep going, there's only like, if the bishops are as far apart as possible, they're in opposite corners, there would only be one square. And you can kind of guess that this is just the sum of all squares from 1 to 99. But if you think about it in a square like this, there's actually two ways to put a bishop. You can either have them in these opposite corners or in these opposite corners, which means you just multiply the sum by 2. And that's an easier way to calculate the total amount of arrangements, I think. And some of this, I think the formula for sums of squares is just, oh no, I ran out of space. The answer would be 2 times 99 times, oh shoot, I forgot, 100 times 199 over 6. And we should be done here. Yeah, so that's a really nice bijection I found while thinking about squares and stuff. Yeah. I don't know the final answer. I am so sorry, guys. But this should be 656 something. All right, that's it.